Good evening, everybody. Welcome back to Night Skies at Home. My name is Derrick Pitts. I'm Chief Astronomer at the Franklin Institute Science Museum, and thank you for joining us tonight for the online version of Night Skies at the Observatory, a great program that we've been doing at the Franklin Institute for quite a number of years now. But due to the pandemic and the quarantine situation, of course, as you know, the Franklin Institute is closed. So we thought it would be a good idea to bring Night Skies at the Observatory to you, but at home. So here we are, Night Skies at Home. This is a program that we hope will help you get outside to enjoy the evening skies right in your own location. So you can go out into your backyard, you can go out onto your front lawn, on your front steps, right at your own home, and you can enjoy the night sky. And you can also use it as an opportunity to begin your studies of the night sky, your sort of like introduction to the night sky, so that by the time we are actually outside again with others, we will have come to a much better understanding of what the sky is all about. You'll be able to find your way around, and you'll be able to understand a lot of the complexities and depth and odd phenomenon that happen out there in the universe. And hopefully you'll be able to share that with plenty of folks when you're outside under the night sky. So this is a program certainly for anybody at any level. Doesn't really matter if you've never looked at the sky before, or if you're not really interested in the very, very deep scientific part of it. Everybody enjoys some aspect of looking at the night sky, and this program allows you to pick and choose what works for you. So if you're just a beginner, this is great because we'll give you some tools to help you figure out how to find your own way around the sky and how to find other resources to help you understand the sky. And if you're advanced, we're going to have some wonderful content for you as well, not only in subjects that we present, but in our guests that we're going to have as part of our program too. So there's something here for everybody. Hopefully, by the end of all this, or as we get further into the year, into the summer, you will be able to be an expert in your own neighborhood. Dazzle your friends and family with your incredible astronomy knowledge. Yep, you too can be a Carl Sagan right in your own block. So stay with us as we go through this, and you'll be able to learn a tremendous amount about the night sky. So tonight, we're going to do the usual stuff that we do. Of course, we'll take a tour around the skies and see what's available to be seen. We're going to figure out what satellites are available, particularly International Space Station. We're going to use that program that we used before called See a Satellite Tonight to show you when the next best opportunities are to see space station. And we have a couple of really good ones coming up. And also, we'll talk about astronomy clubs this evening. You know, around in this region, there are plenty of resources for you to use to build up your astronomical chops and skills. And even though we might not be able to gather in club meetings and things like that, most of these organizations are holding meetings online. So that's a great way for you to connect with other people who are interested in astronomy, and for you to hear some really, really great guest speakers talk about what they do in astronomy. So we'll have that for you. Also tonight, I have a great guest coming from the University of Pennsylvania. Mark Devlin is going to be with us this evening. We're going to talk to him about the astronomical research that he does. And of course, your questions. That's what we're after. We want your questions. If you have questions throughout the evening about how to do it, where to go to do it, what to use if you want to look at the night sky, if you have questions about space exploration, if you have questions about something in particular about astronomy, please send your questions to us and we'll try to answer them for you. So we want your questions. You know, last week we talked about black holes and telescopes, and I'm sure there must be some questions left over from that. So even if you have black hole questions left over from last week, be sure to throw those over here too, and we'll see what we can do to answer those. And you'll see around behind me, I have a couple of telescopes here and some binoculars over here, and I have this really interesting sign over here back over my left shoulder. That's an advertisement for the Franklin Institute's observatory from the 1950s back over here. So maybe while we're sitting here, you'll get a chance to take a look at that too. I'm not in that picture, by the way. I was just barely born in the 1950s, so don't look for me there. Anyway, we have a lot to do tonight, so let's get rolling. First things first, let's just go over our sky phenomenon, just the quick stuff about sunrise, sunset, and the moon, and then we'll head on from there. So sunrise now is coming at 5:45 a.m. Oh yes, very early on now. And we're picking up about 1 minute and 53 seconds every day. We're now slowing down how much extra sunlight we're picking up as we head on toward the summer solstice. You know, it's May 14th, so we're a little over a month away from the summer solstice. So the amount of time we gain every day is going to slow as we reach the summer solstice. That's when we have the greatest number of hours and minutes of daylight. So we get those long summer evenings, and they're really, really great. But I have to warn you, when we get to that point, guess what? We're going to start losing minutes right away again. So you should enjoy this month and a half or so as we make our way up to the summer solstice, so we can enjoy these really long evenings. Sunsets now are coming at 8:08 p.m. and you'll see that extend all the way out to about 8:30. We're at last quarter moon now. It rises at about 2:12 in the morning, and it sets at 12:25 in the afternoon. So that's 25 minutes afternoon. Now, I want you to do something with this. I'd like you to go outside and see if you can spot the moon high in the western sky between 8 a.m. and 9 a.m. So tomorrow morning when the sky is clear, if you head outside between 8 and 9, or if you're already outside between 8 and 9, look up into the western sky, high in the western sky, and see if you can see the moon. It's going to be a waning crescent, and it's going to be difficult to catch because it's the sky's very bright, and there's very little contrast for you to make the moon stand out against the sky. But I want you to notice that it's there. And the cool thing about this is that the moon is visible almost every day of its 1 month cycle. And so you can figure out the time to look, and you can find almost every day. There are only a couple of days when the moon is not visible. There are about 3 days really when the moon is too close to the sun as it makes its way across the sky. So that's just a couple of days before new moon, right at new moon, when the moon is in the sky at the same time as the sun, almost in the same location, and then just a couple of days after that. So other than those days, you can see the moon almost every day. So I want you to get out and see that. We have a lot of great other stuff that we can see. We still have planets in the sky. We have Venus over in the west. And we have those bright planets, Jupiter, Saturn, and Mars over on the eastern sky early in the morning. But that's early in the morning. So I want to give you a little bit of a hint where to look for that. What I'm going to do is I'm going to use our star map program to take us around to take a look at that. And we'll see what that looks like. We have space station or space shuttle sightings coming up. You know, the cycle has now moved around for us, so that we have space station visibility in the evening after sunset now. And we have a couple of those coming up. There is one tonight, a little right around 9:30, but the skies here are cloudy, so we're not going to be able to see it in this region. But tomorrow, when things are supposed to be, I think things are supposed to be clearer, we'll have a couple of sightings then, and one tomorrow night, and then on Saturday, there are 2 space station flyovers, and you can see both of them. So we're going to go over that with great care, so you'll be able to pick up what those things are. Okay, so that's what we're going to do for this evening. So we're looking for your questions. I'm going to check and see if we have any questions right now. We'll get started with a couple of those, and then we'll go out and we'll visit with our friend Mark Devlin. So what do we have?
How fast does a shooting star move?
The question is, how fast does a shooting star move? You know, I really love the name of some astronomical events or phenomena because they sort of describe exactly what's happening in a sense. So this one is the shooting star. It goes by another name, a falling star. But of course, the one thing we have to realize is that stars don't fall and stars don't shoot. They actually don't do that at all. But what we're seeing when we see this actual event is a little tiny grain of space rock, if you will, that's plunging into the Earth's atmosphere. When it comes into the Earth's atmosphere, that little tiny sand grain-sized object creates all the light you see because the energy with which it punches into the Earth's atmosphere heats all of the air around it and causes that air to glow. And that gets very, very bright, and you see it as that bright streak. And when they come into the Earth's atmosphere, they are going fast, 40,000 miles per hour. They are really cruising along. So here's a really great opportunity to invoke one of my favorite mathematical or physical formulas, F equals ma. Force equals mass times acceleration. In the case of these little tiny grains we have falling into the Earth's atmosphere, well, what we have is we have a very small mass. Now, if we had a small mass and a small acceleration, there wouldn't be very much force tied to that. But in this case, we have a huge amount of acceleration on this. So what that does is it multiplies the effect of the mass so that we have a great force coming out of it. And that force, that energy is dissipated out into the surrounding atmosphere to heat it up and to make it glow. And that's why we see what we see. Now remember, these are sand grain size. We can see 10 of these meteors. That's the actual name for these objects. We can see 10 of these meteors as they plunge into the Earth's atmosphere every hour. Occasionally there are meteor showers through the course of the year, and at that time we might be able to see more than 10 per hour. The two best meteor showers are the Perseid meteor shower in August, on August 12th, when we can see maybe 80 to 100 meteors per hour. And then as we come to the end of the year, the Geminid meteor shower in December, on December 14th, shows upwards of 120 meteors per hour. So those are the two best ones, but on any clear night, you should be able to see at least 10. You should be able to see at least 10 per hour. Okay, is there another question?
Lots. What do you do if you have too much light pollution?
Oh, there's a great question. What do you do if you have too much light pollution? Well, this can be a real challenge for folks that are trying to observe the night sky in an urban, a well-lit urban area, say downtown Center City, Philadelphia, or really any community at night. We have lots of street lighting, and that street lighting, of course, helps us to see where we're going. But often that light is misdirected up into the sky, and that can become a challenge for seeing the night sky. So there's two things you can do. Number one, if you're trapped in an urban area and you just can't get out to someplace where the sky is clearer and darker, make sure you try to do your observing away from street lights. So stay away from parking lots, stay away from standing right underneath a street light if you're going to do some sky observing. And any improvement you can accomplish by moving away from those bright lights will help improve your chances of seeing. Now, even in urban sky conditions, you can at least see the brightest stars and you can see the bright planets. So you're good for that. Now, if you're out in a suburban area and you can get yourself even farther away, or I should say it this way, to really improve your chances of seeing a clear night sky, take yourself out of an urban environment and move out to someplace where the sky is clearer and darker. Now, last week, we talked about 8 Pennsylvania state parks that are really well suited for astronomical observing. In fact, they're set up and welcoming for people to come out and look at the night skies, taking advantage of that natural resource of a beautiful night sky at those 8 Pennsylvania state parks. Now, we had a list of them posted last week. They're on our Franklin Institute website. You can go find them there. And PA Tourism would love to have you come out and take advantage of that. If you can't get that, and one of them, by the way, is French Creek State Park, not too far out to the west, a little bit west-northwest of us is where that is. Over toward the southeast, out into South Jersey, there are some great locations down in the Pennsylvania, down in the New Jersey Pine Barrens, and in the farm regions. Hey, you know the back way to Cape May? You know how you can sneak down the back way to Cape May rather than take the main highway down to Cape May? Well, along some of those back roads, the skies get really dark out there. So that's a really great place. And that's only 45 minutes away by car. And the other cool thing I like about that, there are Wawas along the route. So you can stop for coffee and snacks and stuff like that. So it makes it a really pleasant journey to do that, okay? So there are regions around, not too far away, where you can find some clear, dark skies. We have time for one more.
Okay, do you think there will be manned missions to Mars in the near future? And what technologies are needed to make a mission like that happen?
So the question is, do I think there will be manned missions to Mars in the not too distant future? And what kind of technologies are going to be needed to make that a successful mission? Oh my goodness, there's a 2-hour program right there. I do think it's going to happen in the not too distant future, but there are a lot of technologies that are going to have to be developed to mitigate a lot of the challenges that humans have for long duration space flight. There's so many of these issues that have to be figured out before we can actually send people on a long trip to Mars. And the reason why is because the absolute shortest mission that we can get people out to Mars and back is 1.5 years. That's the absolute shortest time. And that's if they only spend a few days on the surface of Mars after traveling for months. So, since we have not had many people in space for more than 1 year, in fact, Scott Kelly, just a couple of years ago, spent 340 days in space. That wasn't even a full year. if you read his book about his experience, you'll realize how many challenges we have before us in terms of getting the human body properly prepared or being able to mitigate all of those space travel challenges that the human body isn't really built for. All of those things have to be fixed. And one of those problems is something we're having a difficult time with right now, tongue in cheek, of course. But you know what? If you're going to go to Mars and you're going to take that long to get there, you're going to need 1.5 years worth of toilet tissue at least, okay? So I'm just saying, these are some of the challenges we have to face, okay? You can figure out the rest of the challenges from there, okay? All right, great. We'll come back and do some more questions in just a few minutes. But I want to welcome my good friend Mark Devlin, who's going to join us right now. Mark is the Reese W. Flower Professor of Astronomy and Astrophysics at the University of Pennsylvania, right here in Philly. And Mark is a astronomical researcher par excellence. He does all kinds of really great stuff trying to help us understand the story of the universe by collecting data from the universe in lots of interesting and different ways that you may not have expected before. So here's one of my favorites, and it refers to a project that Mark did a number of years ago now. It's called the BLAST Project. And this is a project in which he and his team built a detector that was then flown up into the high atmosphere of Earth using a balloon from Antarctica to reach the altitudes needed to collect the information he wanted to get to help build out this picture. So hopefully Mark will tell us some more about that as we chat with him tonight. Good evening, Mark. Thanks for joining us.
Nice to be here, Derek. Thanks again.
Yeah, thanks for being here. I have been watching what you've been doing over the years from the Franklin Institute, and it's really remarkable for a number of reasons. Not only do you collect all this really wonderful information in an effort to better understand some things about the universe, but you do it in such a really interesting way with your students building all these great instruments. And you sort of share all of that really fun and excitement of research and exploration and discovery with your students in a really great way. But why don't you first tell us, if you will, please, I'm interested in the project and what you do at Penn right now, and tell us about the project that you're working on right now, and then we'll circle back to the balloon story in a few minutes.
No problem. We have a whole bunch of things going on at Penn, not just in my group, but over in the entire department. We in the what we call the experimental cosmology group, which is my lab in the David Rittenhouse laboratory. We're working on a number of things. You mentioned one of them. BLAST is still going, even though we seem to destroy it every few years. We build it back up and fly it again. The main project that's going on right now is something called the Simons Observatory. It's an enormous cosmic microwave background effort funded by Jim Simons from the Simons Foundation in New York City, and it's the first time I've ever done something quite this big and really I would say just ambitious in its scope. I've been.
Well, wait, hold on. You have to break this down for us a little bit more, because I heard the words go by cosmic microwave background.
I'm going to get.
Wait.
Okay,
Okay, go ahead.
So what we do is basically my cosmology research is studying the early universe, and what we're interested in is the story of the universe over cosmic time. And what I mean by that is when you go out and look in the galaxy, or the astronomer or anybody who goes out and looks at the night sky, even from Philadelphia, you're going to see a bunch of stars out there, and you're going to say, well, that's pretty neat. And what a cosmologist wants to understand is, how did it get that way? How did the stars get that way? And more importantly, how did the galaxies get that way? Because there's many, many galaxies out there. And how did it get that way over the course of the age of the universe? And really what that comes down to is that when we look out in the universe today, you see a very structured place. I mean, the Earth is round, right? And that's a structure, but moreover, it's dense. And next to the Earth, it's not dense. There's nothing there. And our solar system is nice and compact and nice and warm, but you go next to our solar system, there's nothing. And then you go to our galaxy, it's very nice and compact compared to next to the galaxy. And then you can look at it and say, well, there's now our local group of galaxies, which is a couple dozen galaxies. They're all kind of near each other and clustered together. And then you can take that and go to even larger structures, getting up to hundreds of millions of light years in size. And I look at that as a cosmologist and say, okay, well, that's structure. How did that form? How did it get there? And then you go back and you say, what is the furthest I can look back in the universe? And for us, that is looking at the universe when it was about 375,000 years old out of its 13.7 billion year age. Okay, so it's fairly young. And as a cosmologist, we also consider it to be very hot. In fact, the average temperature of the universe at that time is around 3,000 degrees Kelvin. Okay, 3,000 degrees above absolute zero. So, and essentially the same thing in centigrade, but very, very hot and glowing. And that's what we call the cosmic microwave background. And when we observe that, we say that's what the universe was like just after it was born. We see that there's the structures that we see today don't exist. It's very smooth. Everything's the same to about 1 part in 100,000. So you look at one chunk of universe, it's the same as the piece next to it to 1 part in 100,000. Whereas you look at the Earth, obviously next to the Earth, it's very different, and the density contrast is huge. And so cosmologists ask the question, how did it go from being that very, very smooth universe to being the very kind of organized and lots of density fluctuation universe we see today? And so that's trying to understand how it evolves over cosmic time. Now, you might just say to yourself, well, gravity just pulled it all together. You know, gravity sucks the Earth into a ball and gravity sucks the sun into a ball. And that's a really good model. And it's a starting point. You start with gravity. You say, can gravity make the universe happen? And you throw gravity into it and you say, not enough time. Can't do it, right? There's just not enough time between that 13 billion years isn't enough to make the universe that we see today. So what cosmologists do is we throw in lots of things into the model, one of the biggest ones being dark matter. And you've probably discussed dark matter before in the show, but dark matter comprises about 30% of the universe, and it's about 10 times as much dark matter as there is normal matter. And so you throw that into the model, you throw, you know, like I said, gravity, you throw lots of particles in there and so forth. And if you do that, you can make the universe. You can make the universe we see today. The problem with that is that there's lots of ways of combining all those different things to get to the universe we see today. Because there's lots of different ways you can tweak the knobs. You can dial this knob this way, this knob that way, and make it all happen. And that's not satisfying to people like me. We want to know which knob is in which direction. We want to know which thing is exactly the way it is. And the analogy would be if I said, Derrick, I want you to drive to LA tomorrow, and you could choose any one of a number of paths to get there. You could, you know, go north, you could south, you go directly east or west, I should say, and you can get there. But if I told you had to pass through the following 30 cities on the way, then your path would be very well defined. And what we do as cosmologists is we don't just measure the beginning point and the end point, we measure it at many, many points in between. And when we constrain it to have to pass through all those points, we essentially dial in those knobs to be exactly where they were. And our job is to understand how these parameters work in the universe, to understand how we came into being. So that's the basic idea of what we do.
Okay, wow, yeah, that's incredible. That was very well done. I understood everything you said there, so it was good. And they were great analogies, but I have 2 questions for you. So the idea of dialing the knobs to create these universes, I mean, or to create the universe that we have now, does it matter how those dials are set? I mean, you sort of hinted at the fact that the knobs seem to be set in just such a way that we have the universe we have. Would the universe be different if we changed any of those knob positions?
Well, that's exactly the point. If we measure the way the universe is, and it can't, once you measure it as it is as a function of time, it can't, well, the idea would be that it can't be, the knobs have to be in those exact positions. But if you just have 2 points at the beginning and the end, then you could have different things going on to make it so. But you know, we want to understand how gravity works, for example. That you could put that in as a knob. You want to change that. The amount of dark energy, you may have talked about that in the program before. The amount of dark matter. We'd like to understand how those things function. There's little tiny particles called neutrinos, which are pervasive in the universe. We would like to understand how the mass of those might be affecting how the universe evolves. So there's so very much encoded in this information about the universe that's really fundamental to understanding physics. And the reason is that you might say, oh, just to use the mass of a neutrino, for example, suppose I change the mass of a neutrino by 10%, who cares, right? Well, and what effect would it have? Well, the thing is that it's not that it has an effect on, you know, what happens today or tomorrow, but you're integrating that effect over 13 billion years. And so even the tiniest little change can change where you end up at the end. So it's like changing
It's cumulative.
the slope of a line, and then saying that line ends up in a completely different spot. So, it's a very, I would say, exquisite way of understanding how things go.
Okay, so now let me ask you this. Here's my second question for you. You alluded before to, looking at the cosmic microwave background, that very, very hot, very, very bright period when the temperature was 3000 Kelvin. So when you're looking at that back over time, you're looking way back to this early time in the universe, 345,000 years after the beginning of the universe, or 375,000, give or take, 10 or 20 years here and there. But my question is, though, that's a long period of time and a long distance over which you're observing. How is it that you are sorting out that signal from any other signals that must be in between your observing point here and what you're looking for out there?
You're basically talking about my life, is dealing with that. So I mean, it's a really important question for us. We call those it's a kind of funny thing. We call them foregrounds, because when you're looking at the cosmic microwave background, everything is between you and it. And so and so you might think of stars as being very far away, but I would think of the dust around stars as a foreground. They're just between me and what I want to see. And and there's a couple of things that you need to understand about that. Is that light, if you look at a star, for example, like our sun, you see it looks pretty like white light. It looks, like it's a uniform thing, but it really is. It's made of a bunch of colors, and we call that a spectrum, which means that there is a distribution of different frequencies of light, and we can really understand that very well. These things which are in between us are predominantly in our galaxy, so very close to us. It turns out it comes from emission from essentially dust, really small, like micron-sized grains of carbonaceous material, which is a byproduct of the evolution of stars, is kind of filling up just around in our galaxy. And that stuff emits light, it turns out. Not light that you can see with your eye, it's not visible light, but it's light that interferes, it's very close to the frequencies that we look at for the cosmic microwave background. But it's got a very, very different spectrum. And so it's got a very, very characteristic signature in the frequencies of light it puts out. And so what we have to do is we can't just measure at one frequency. We've got to measure at a whole bunch of spectra, frequencies, to get the spectrum of the light, and we can discern which is coming from the cosmic microwave background and which is coming from this foreground. And the other thing you need to really understand is that while stars are very bright to your eye, if I look at a star with my telescope, we don't see it. It's just completely blurred out, and it just doesn't. It's such a small signal for us that it's irrelevant compared to the cosmic microwave background.
And so you have to know what signal you're looking for so that you can sort it out from all of the other signals that are coming in.
You bet. And you might say that's a little suspicious, because if you know what you're looking for, why you're looking for it. And the thing is that we understand the basic characteristics of we call it just basically the temperature of the cosmic microwave background. And that gives a very, very specific spectrum. And what we don't understand is the spectrum of these things that you're talking about, like this dust or something else we call synchrotron radiation. We don't understand those so well. So we actually have to characterize them very well. So half of what we do is making a really, really sensitive experiment. Remember, we're trying to measure these days temperature differences on the sky measured in 50 nanokelvin. So, really, really small temperature changes.
I can't even imagine what that is.
Well, it's really small. I mean, we're talking 50 billionths of a degree, right? So it's a tiny temperature fluctuation. And to do that, you not only have to have a very sensitive instrument, but you have to be able to, again, remove these other things that could be confusing. There was a very famous experiment about 8 years ago, which announced a really big result, Nobel Prize winning kind of result. And it turns out that they had not actually removed one of these foregrounds correctly, and they had misinterpreted it as being the actual signal. And that was a problem. And we now we're understanding that, and we're going deeper and deeper and deeper. And part of the Simons Observatory's goal is to get deeper than anybody else has ever gone. So as sensitive as you possibly as we can get with this telescope, which is not quite the ultimate sensitivity, but getting very close to what you can do for the cosmic microwave background.
Now, working with these particular instruments, though, two things. First of all, they are not the typical kind of telescope that people are used to, that the general public is used to understanding as a telescope instrument. They're very, very different from that. And then the other thing is that it's not just you. You're not doing this alone. You work with enormous teams that come together from all over the world to bring their talents to bear and their interest to bear on this too. And you all do this in unusual places around the world. Tell us some about that, about those parts.
So let me tell you about the team. When I was in graduate school, which is a horrifically long time ago now, but the team really was, there was maybe 5 people, 6 people. And I would go to the coffee shop in the morning, get my cappuccino, go in the lab and my detectors one by one. I could name my detectors. There were like 5.
Wow.
The instrument that we're building now has, the capability of having 80,000 detectors in them. Right, so you're going from 5 that I made in a microscope by hand by myself to now building 80,000 of these things. And it went from an instrument where a student could design it, build it, field it, and analyze the data with just 5 people, 5 of their peers, to something which is now my current experiment, the Simons Observatory at Penn. We have 4 or 5 graduate students and 2 staff scientists and postdocs. And we're one of maybe 8 universities in the country working on this. But the whole project size is more like 30 institutions with 300 people. And so we're not only building the telescopes, we're designing really sensitive cameras. In order to get the sensitivities that we need to cool our detectors to about 0.1 degrees above absolute zero. And so in a couple blocks from where the Franklin Institute is, in our high bay where we're building this receiver, it's the biggest one ever made. It's the size of a room. We're cooling 2,000 pounds of material to 4 degrees above absolute zero, and about 300 pounds of material to 0.1 degrees above absolute zero. I mean, this is just doing that is a feat in itself. And then we have another team at the National Institute of Standards building the detectors, another team building this, another team building that. It all comes together into this huge effort to achieve this one goal. And and that's kind of fun. Now, the problem with this is somebody mentioned light pollution, right? Polluting the sky. Well, we have a problem. We have a much bigger problem than that. We're not worried about light, but we're worried about the atmosphere, period. Right, so the atmosphere is a real problem for us, and ideally, I would love to put my telescope in space. But space, you might have guessed, is a very expensive place to get to, and our telescopes are quite large. The one we're building right now is 6 meters in diameter, so that's obviously it's much bigger than the Hubble Space Telescope, and it's just very expensive too. So we like to get to near space. And you mentioned my experiment called BLAST, which has a different goal. That gets above most of the atmosphere. About 99.5% of the atmosphere is below you. So you're looking through only 0.5%. But the experiment that we're talking about, what was that?
I was saying that's good. That's good to get that high.
It's good. Now, we're taking the Simons Observatory we built at a site which we've been developing for our other experiment called the Atacama Cosmology Telescope. And you might have guessed it's in the Atacama Desert down in South America, in Chile. And it's at around 17,000 feet. And at that point, there's about half the atmosphere is below you and half the atmosphere is above you. So it's about half atmospheric pressure. But it's also incredibly dry. And water and water and oxygen, basically, of course, we like them to live, but they're very bad for observing the cosmic microwave background. And so we get rid of a lot of the oxygen, of course, because we're very high. And because it's a very dry location, most of the water is gone. And so we can do not what you can do from space, but you can do a really good job, and you can be years doing it. So we've been operating an observatory there since 2006. And this new one will come online in about 1.5 years, and we'll operate it there for as long as it takes to get it to go.
Wow. That's great. Now that's a really challenging environment to work in the Atacama Desert. You mentioned that it's at 17,000 feet. It's not so good for humans to be in. It's great for the instrumentation because you have so little atmosphere above you. And you're right. It certainly does reduce the cost of getting the information you need rather than putting it into space on a rocket, because there's all kinds of risks and costs involved with that. But at the same time, it's challenging for all of you as astronomers to be in that environment to work. I've been down to the radio telescope in the Atacama Desert that is at 17,000 feet. Yes, right. And the one thing that that certainly was challenging to all of us who were just going there for a visit is that, well, that telescope I think is 16,400 feet up, and
we look down on them.
You look down, right?
So to speak.
Right. You look down on Alma.
They're just a little bit below us.
Right. Just a little bit below you. Yeah. Okay. All right. I get it. But it's challenging for humans. In fact, I know this, and you probably know this, but I think our audience doesn't realize that these are big dishes that they have. 66 of these 12-meter dishes that they have out on the desert floor up there. Again, taking advantage of the altitude and all this other sort of stuff. But if they need to work on a telescope, they take a huge truck up to the site, and they actually pick the whole radio telescope up off of its mount and bring it down to an 8,000 foot altitude, or bring it down 8,000 feet. No, down to 8,000 feet. They bring it
down from 16,000 feet to about 10.
So that, and they can work on it there where the environment is a bit more accommodating for humans. Right. As I understand it, they don't like to have people up there working for more than 3 hours at a time, up on the high site. So they like to, come down to that. So I would imagine that this is, I think it's unusual for people to understand that this is a piece of modern astronomical research, particularly in the realm that you're working in for the kind of data that you want to collect, where you really need to be at these locations.
Yeah, no, you have to go where you got to go. I mean, like you said, I've been to Antarctica 5 times. I think my collective time on top of that mountain is probably way in excess of a year on top of the mountain in Chile. Because I've been going there since about 1998 with various experiments over the years, and before I had children, I think I spent 2 months at a time on the mountain, and so we don't live up at 17,000 feet. We live at around 8 or 9, and then we spend I'll spend 12-hour days up there and work, and then
wow.
One of the reasons they bring the telescopes down for ALMA is it's because of what you said. It's difficult to work up there, but also it gets snow occasionally. It's much more reliable to be down low, and you have access.
Yeah.
Get access all the time.
That's true.
So they bring it down a bit. I can't bring my telescope down, so we have to go up.
And these are, and like you pointed out, these are. You pointed out that there's very little moisture in the atmosphere, but the other thing at those altitudes, you mentioned snow. But there really isn't very much precipitation up there either. In some of these places, it hasn't rained for 100 years or more in some locations, and so these are ideal for that kind of work.
We're kind of in our wet season right now, but wet meaning nothing so far at the site. But we call it the Bolivian winter. So occasionally the dry lines will move up, and we get some snow. But it doesn't really take much at 17,000 feet to ruin your day. I mean, 6 inches of snow when you're trying to go up a really, really steep road, that's dirt road, you get a drift on there, you can't get up, and it's too difficult to get there. So we just kind of shut down when it's like that, and we just start back up when it goes away.
Yeah. Now, Mark, you work with a lot of students. I remember we talked once before about how you like to involve a lot of graduate students in these projects to give them an opportunity to have experience designing and building big instrumentation that they can use for astronomical research. So you're really giving students a great hands-on experience at building this instrumentation. Can you talk about that for a little bit?
It's not all benevolence on my part. The telescopes are built, the design, the current instrument that we have right now, this camera, which is again the most ambitious camera that's ever been attempted, was completely designed and built. Well, we had a company weld it, but the entire design and the integration of it was done by graduate students and some postdocs. Postdocs being people who just graduated and got their PhDs. Now, when you say students, I mean, let's be clear. These are people who are 22 to 28 years old. They're adults, right? But very, very talented. And I think the thing is, you've got to think of it as training to go on to the next, to do next thing. And you know, these are big complex projects, and the students who work on them get to understand from the concept, the scientific motivation for it. How am I going to do it? So you have to come up with what's required to make it happen, decide the method about what you're going to go about doing it, and then as they get more and more ambitious, as this is, and very expensive, you can't make mistakes, right? You can't just say, oh, well, I got it wrong this time, let's go back and do it again. You have to do it right. And so there's this whole process of reviewing how it goes down. How do you build it? You actually get people to come in who aren't involved, and they review it. They criticize you. They say, why'd you do it that way? You should be doing it better this way. And then you build it and you test it. So we're right now in the testing phase of this thing. So we built it. It's kind of, if it weren't for being locked out of my lab, it would be the most fun you could ever have, right? Because we're proving all the things that we've been working for the last 3 years to do are all now coming together into one spot, and they're going to work. And we're missing the detectors, but they'll be coming in. Well, they would have come in this fall, but they'll come in, and then we'll put it all together and we'll test it. And it's going to be a great time, I hope.
So, Mark, I also know that in doing this work, there are occasions when things go wrong. Not everything goes perfectly right when you're trying to get these instruments to work. Is there a particular instance that comes to mind for you of when something has not performed exactly as it should, or
well, there are so
things
many.
Didn't go the way they should?
I would say it's embarrassing, but it's not embarrassing. It's just part of the process.
Right. That's a good point.
You mentioned one of my more famous ones. It's the BLAST experiment, which this is now getting kind of old. The story was in 2006 when we flew it in Antarctica. You fly in a NASA altitude balloon. These things go up, and we have a lot of data that we take, and it's too much data to get through the satellite network. So we have to record it on hard drives. And we had gotten up, this is now after working on it for 5-6 years. It was up there and it was working great, we could tell. And it flew around the pole. So it was about 14 days later, and we decided to cut it down. And it landed, and the parachute didn't separate, and it dragged my telescope 140 kilometers or something like that, and dropped off little bits and pieces of the telescope along the way. But the story is it's actually chronicled in a movie called you might expect Blast, and you can take a look at that. But more recently, we just got back from Antarctica a few months ago. And again, a similar kind of effort to build a very complex piece of instrumentation. And they launched the balloon, and there's part of the balloon launching process releases what they call the collar, but a piece of equipment drops, and it's normally supposed to miss the telescope, but this time it hit us and did some pretty significant damage. And so, which made it so it didn't work. And so you're talking about, watching 5 years of work kind of dissipate pretty quickly. And but as you said, it's not a loss, right? Because on the way, we trained, a dozen graduate students and postdocs and so forth, and we developed technology that we can use for our next instrument. And so while we didn't reach the science goal, if you treat it as a total loss, you couldn't move, right? You'd be so devastated you couldn't do anything.
Of course.
You have to say,
sure.
Yep, but look what we learned. These worked, this worked, all these things worked. Yes, that we got hit by this piece of equipment and it broke it, but next time we won't let that happen. And you figure it out and you make it go. And that's the advantage of doing ballooning with NASA, is because they kind of give you a pass, right? It's supposed to be risky. And if I launched a satellite and it broke every time, they'd be kind of upset.
Oh, that'd be different. Yeah.
But
they might not be so happy about that. Right. Well, that's, it's important that you bring out that this is part of the process. It is all learning, it's all training for what you're going to do better next time, so that you can have a better result. And I think one of the things about science that people really need to understand better, I think, is what this process of science is that we do, and why we do it, and why we depend on everybody, everybody around us, all of our fellow scientists, to work with us, to help us, clean up the work that vet the work that we're doing, look at the work that we're doing, to help us figure out areas that we may not have been able to catch before, and all being in an effort to get to a goal that we pretty much mutually want to help each other achieve, because it's building on knowledge that helps us better understand the universe that we live in. It must be, you must feel like a special part of that work.
I think we're all pretty happy to be doing what we're doing. Very privileged to be able to do this kind of stuff and just keep it going. I mean, it's just like I said, it's a lot of fun.
Yeah, that's great, and it's not cheap either. You know, it doesn't cost a little money to do this kind of stuff.
That's right.
But
Well, we have Jim Simons helping us out right now, but also the National Science Foundation. I've only mentioned two of my projects. We have another project that goes to the Green Bank Telescope in West Virginia, which is the largest movable telescope on the planet, and various other projects that we do. Those are our main ones. And but it's funded by, again, this private foundation, the Simons Foundation, the National Science Foundation, and NASA are very good. But the NASA and National Science Foundation are, they're science driven, but they're also want to develop technology. They want to develop people. When one of my students goes off and gets a job and even in industry or with NASA or something like that, every single one of them is a success, right? Because we've trained them, and the reason they're valuable to the places where they go is because I hope is because they've taken a lot away from the way that we do things in these laboratories and in the field, not just from the technology, not just from the science, but just the way you approach problems and solve things.
Mark, that's great. This is incredible work that you're doing. I'm sorry we don't have more time to talk to you about some of the other projects. I hope we can have you back again sometime in the future to talk about the other stuff and give us some progress reports on what's happening down in the Atacama Desert. I often say that most people around this region have no idea the depth and the quality of the astronomical research effort that's being mounted right here in the Delaware Valley, and the work that you and your colleagues are doing at Penn, even in collaboration with everybody else around the world, all the rest of the people on the team, is truly remarkable. But this is happening right here in Philadelphia. I'm extremely proud that this kind of stuff goes on here. And I often say to people, we should really think of Philadelphia more as a science city than as a sports city, because there's so much tremendously advanced science going on here in Philly. And the other thing I say about it is we really should think about it as a science city because, in science, you can't lose a game. So it works out better if
We're always making progress.
Think of us.
Right.
right. So Mark, thanks a lot for being with us. I really appreciate you joining us. Remarkable stuff. And hopefully we'll catch up again soon. Good luck in your projects. And I'll see you over in Narberth sometime soon.
Certainly. Okay. Thanks, Jim.
All right. Take care, man. Thanks. Well, folks, I'm really glad we could have Mark Devlin with us. He's the Reese W. Flower Professor of Astronomy and Astrophysics at the University of Pennsylvania. He has these great astronomy projects going on. You can look him up at the University of Pennsylvania's website, Devlin. If you go to the Penn's website, you can look him up under the faculty and see what kind of work he's doing. And if you look for some of the projects we spoke about online, you'll find some information about that too. We'll put some stuff together and put it up on our website so that you can delve more into some of this amazing stuff he's working on. It's really incredible. So I'm sure you might like to learn more about that. Okay, folks, I know you have some more questions. So let's take a couple of questions. And while we're taking some questions, what I'm going to do is I'm going to bring my laptop over here so that we can bring in some additional resources that we can work with as well. So let's start with some of those questions. What do you have there, Linda?
All right, we can't see you. Can't see it. Tips it down a little bit. Okay, when will we be able to see the Comet Atlas?
Oh, the question is, when are we going to be able to see the Comet Atlas? I have bad news for you about Comet Atlas. It was looking great, as if it was going to be visible this spring. In fact, it looked like it was going to be visible this month. But as it turns out, Comet Atlas broke apart a couple of weeks ago, fragmented into a number of different pieces. And so it didn't hold together as a complete whole nucleus. So surface brightness went down, and we're not going to be able to see any more of that. There is another comet that's available in the spring sky right now. We're going to go online and see if we can take a look at that and give you the name of that so that you can go out and take a look for that too. But I want to warn you, it's not as bright as people have been saying it's going to be. So don't expect that this is going to be a binocular object. Let me put it to you that way. You'll have to be out in the pre-dawn sky to see it. It's not spectacular. So don't expect, if you do go out to see this, that it has a long tail and all that kind of stuff. It's not going to look like that. But we'll cover that anyway. So, so unfortunately, Atlas is not the one. But the next one that comes up, we'll make sure you know about that. Okay, so, you know, I mentioned earlier that we had a couple of other things that we were going to take a look at. So here's what I'm going to do. I'm going to share my screen now, and I'm going to jump out here over to my desktop. There we go, right there. And we're going to come out here to my other screen, right out here, just like this. We'll move some of this stuff out of the way so we can see, because earlier, you know, we spoke of satellites that we might be able to see coming up soon. So let's jump right into the International Space Station stuff so you'll have a good idea about that. So the program that we're using here is called See a Satellite Tonight. You can look it up under that name, See a Satellite Tonight. And if you search that in any search engine, you'll come to this website, james.darpinian.com, but just look for See a Satellite Tonight, and you'll come up to what you have here on the screen right now. So the first one I mentioned is at 9:38 p.m. tonight, and I'm going to show that, and you'll see here that over on the left side of the screen, you can see International Space Station as it approaches your position on the planet, and it even shows you where you'll see it in your sky, in your neighborhood. That's a really cool thing. This view right over here on the right side shows you your street and shows you where in your neighborhood you can see it. Now, again, that's tonight, and unfortunately, the skies here are not really clear enough. I'm going to jump to tomorrow night across these other ones because, as I said, I think there are, let me see, there's a rocket booster right there. There's another Atlas Centaur rocket booster. And then at 10:36 tomorrow night, you can see International Space Station nice and bright flying across the sky. And there's a nice long view of it, actually. And we can rotate the view here to see that it's a full pass that goes all the way across the sky. So tomorrow night, 10:26 p.m., there's going to be a nice long pass of International Space Station. If the weather doesn't turn out to be satisfactory, there are two views coming up on Saturday evening. Let's see if I can pick out which ones they are. Here, let me see now. Oh, here's the one I was really looking for. Two objects are visible at the same time, International Space Station and another rocket booster, as you can see here on the left. And you can see there's International Space Station right there. The rocket booster might be a little bit more of a challenge to see. But again, the two views you have are where these objects are flying over the planet relative to where you are, and then where you can see them in the evening sky when you go out to look in your own neighborhood. So if you take a look for those on this website, you'll be able to see it there, space station coming by in this view. And using this program, I think, will be a great help in getting you to recognize what these objects look like and where you can see them without much difficulty. I really like this program because it's so graphic and so representative and so easy, works so easily to show you where to look. I want to thank my good friend, Dan Amoroso, a great friend of the Franklin Institute, for suggesting this program. He sent it to me one day, and I really like this program. So thanks a lot, Dan, if you're listening, for sending us this program. So there are a number of other satellites that are available, as you can see right over here on the left-hand column. You have a list of the satellites that are available, and you can pick the ones that work well for you. Okay, so let's now go out into the evening sky, because there's a couple of things I want to try to catch up with you on that sky. So let's go to this first one right over here. So I'm picking this window because this is at about 9:30 p.m., good for the next week or so. If you go outside to take a look at the evening sky, start looking in the western direction, as you can see my pointer right here pointing out, you can just see the last gasp of Betelgeuse, that red giant star that's at the top right shoulder of Orion the Hunter. You'll see Venus is getting down pretty low now at 9:30 in the evening. So if you don't want to miss it, you'll have to catch it in the next week. And right up here, we can see two bright stars of Gemini, Castor and Pollux, right up here at the top of this, right at the top of the twins of Gemini right here. And while it may be difficult for you to see the twins, the shapes of the twins, these two stars mark their heads. These stars down here mark their feet. and their bodies are right here in between. And if we add the artwork, you can see what the twins look like right there. There they are right there, standing right there. Next to the small dog over here, Procyon, and of course Capella over here on this side, and a few other constellations around. We'll let the art go. That's the evening sky right there looking towards the west. I'm going to bring this back around to the south, just like this, right around here. Great view for us right here. We can see the main constellation of the springtime sky that I think is really worth knowing is the constellation Leo the Lion. I'm going to tilt us up in the sky so we can see where that is. Right up here, right around the top of the sky, right there is Leo the Lion. That's the main constellation you can use to find your way around to other constellations in this portion of the sky. So if you use this Stellarium Web Online Star Map, this will help you get started in viewing. Now, when you go out to view the evening sky, as I've said before, don't take more than 10 minutes per evening unless you really want to be out. What you really want to do is build up your skills week by week or evening by evening when you go out. Start looking for the thing you saw the night before, find that, and then move on to another object that's nearby. And that way you can become familiar with the sky really quickly. There's still bright constellations in the west that you can use to find your way along. And of course, you can see from Betelgeuse, you can come right to the top of Gemini and then head into Leo. And that'll take you back across the sky to the east over to this red giant star called Arcturus. That's easy to see as well. Next thing you know, you'll be off into the summer sky. So we have those things that we can see without too much difficulty using these programs. Now, as I mentioned a little bit earlier, you know, if you're looking for more resources to help you learn about the night sky, you can use Astronomy Clubs. There are a number of Astronomy Clubs around the Delaware Valley. In fact, they're all over the country. But right here in the Delaware Valley, we have 1, 2, 3, 4, 5, 6, 7 really, really great astronomy clubs that you can get connected with that can help you build your skills as an amateur astronomer. You can learn about telescopes, you can learn about all sorts of other observing projects, and you'll have an opportunity to talk with people who are also very much interested in observing the night sky. And they're all around the region. There's the Delaware Valley Amateur Astronomers, a really great club that meets in Montgomery County that you can connect with. They have lots of activities everywhere from astrophotography to star parties for the general public. The Rittenhouse Astronomical Society has met at the Franklin Institute for decades, associated with us down there. That's another group that's been around for a very long time. They have a very long and illustrious history. The Bucksmont Astronomical Society across the counties of Bucks and Montgomery County is another great club where there are plenty of dedicated people who know what they're talking about observing the sky and using the telescopes. Chesmont Astronomical Society, also a great club that has tremendous resources for helping you learn about the sky and become involved in activities connected to sky observing. The West Jersey Astronomical Society, in case you're looking for something in New Jersey, is a great club that's been around for a long time. Lehigh Valley has an astronomy club, the Lehigh Valley Amateur Astronomical Society. They even have an observatory up on South Mountain, just outside of Allentown. If you're in that region, I highly recommend you check them out. And last but not least, there's the Delaware Astronomical Society down in the state of Delaware, or right at the state line here of Pennsylvania and Delaware. And you can check them out also. They also have access to an observatory. So there are plenty of resources around of astronomy clubs that can help you. These are organizations chock full of people who are enthusiastic, knowledgeable, and tremendously experienced at working with the night sky. So almost anything you're interested in learning about or gaining more experience with, the folks at these astronomy clubs will help you with that. We'll have this information posted on our website as well. So we're just about getting around to the end of the evening here, folks. And I want to just remind you to go out and take a look at the evening sky whenever the sky is clear. You'll certainly enjoy it as the weather is getting warmer. It's a wonderful time for you to get outside and do this. The cool thing about doing the astronomy stuff right at home is that you can do it from your backyard. You can do it from your front step. You can do it with your family. And you can make it a family project to learn more and more about the sky every month, every week if you join me here. And you can share these experiences with your other family members in other places around the Delaware Valley region. In fact, you can share the experiences all across the country with other family members stretched across the country because, you know, the sky here is going to be the same as the sky in California just a couple of hours later. So you can share some of those experiences as well with them. So I want to thank you very much for joining us tonight. You know, if there's anything that the COVID-19 pandemic has taught us, it's that science really matters. Even while the Franklin Institute is closed, we're still finding new ways to continue our ever important mission of sharing science and technology education, just like this program that you're participating in now. Thanks again for being with us. If you're able, we would be really, really grateful if you'd consider donating to the Franklin Institute today or any other day. Visit our website, fi.edu, and click on the link in our post to give a gift. We would really, really appreciate that. As always, we thank you for your support. It means a lot to us to have your support. Thanks again for joining us now. Remember to take just a few minutes to catch up. And thanks for your great questions. Do we have any more questions there, Linda? While we're sitting here, I think we have time for maybe one or a couple more questions. That's fine. We'll come back and we'll do more questions with you next week. Thanks again for joining us. Next week, space exploration takes a giant leap forward. In a few days after that, we want to get you all prepared for that. Don't forget to check out our website, fi.edu. Click on the link for the Franklin at Home programs. We have such a tremendous array of great programs, short programs, long programs, all kinds of great programs about different aspects of science, just like we do at the Franklin Institute that I know you'll enjoy. And of course, you can follow me on Twitter. My handle is @CoolAstronomer. I'll be throwing out posts every now and then to help keep you up to speed on what's happening in the evening sky. Thanks again for joining us. Best wishes for clear skies until next Thursday. We'll see you then.